morning class. Welcome to today's class, and we're getting ready to stream YouTube Live at the same time. So you should be able to view the live session now. I'll post again a link. Just 1 second. Let me find it for everybody. All right, the link is now there, and I'm gonna mute myself on the Zoom, but if you have questions, feel free to ask. Okay, so for today's lecture, I'm glad to let everybody know we're on the last lecture of the thermodynamics and polymer solution. So today's particular lecture will be focusing on a summary of the whole chapter as a general. So we're going to go through what have been discussed throughout the whole lecture. So we're going to discuss what's going on throughout, particularly the chapter 7. And with some of the time left, we're going to talk a little bit about two problems. First is what is on the essential level is a chi parameter and how that is defined in another way using a cohesive energy approach. And you can actually look up a solubility parameter and compute what is the chi parameter. The second I want to discuss is a little bit about the concentrated region is an extension of what we have learned about thermodynamics, but it's more in realms of when your polymer is more concentrated, okay? All right, let's get started. I want to start with the first one where we talk about the concentrated region, then we're going to go back. I do have a comment on participants, and looks like one of you was not muted, and okay, now it's just thank you whoever just muted yourself. It's much better now. Okay, so what is now new about the concentrated region, and why we should care about this is what we have discussed in previous field lecture is mostly in very dilute, either in the semi-dilute region or concentrated region. So how do we define if a material is in dilute or a little bit more concentrated region? It is depend on the parameter we call it overlapping concentration. So imagine like this lecture, on this lecture we have see that each individual polymer coil is represented with yellow color, and you can see that this yellow color coil is surrounded by red. These dots represent the solvents, and if you see those right now, all these polymer coil are floating around, not overlapping or touching the other polymer coil. They have a safe distance between these two, but as you increase the concentration, dissolve more and more polymer coil, you start to have this overlapping of these different coil, and we have a representation shown here where you have polymer coil touching each other. And in the Chapter 6, we had a homework on this topic, ask about what is overlapping concentration. Basically, we can calculate out what is a concentrated region for this individual polymer coil. So inside this pervaded volume, we can understand how much mass is presented there, because you know what is the molecular weight or degree of polymerization. You can also calculate out how much volume they're occupying. Using this, we can obtain quite obviously what is concentration within individual chain. And we have done this before, so this is where you can use a RG as a way to calculate the volume within it. It's going to be 3,4 pi RG square, not square, a cubical. This allows you to calculate how much volume you have, and you know the mass. Combining those two would allow you to calculate this parameter overlapping concentration. It is defined by C star as here. And this have some significance in your physical property of the polymer. So one of the easy way you can understand is study the viscosity with respect to the concentration. There is also quite a classic study. So for example, where you can plot viscosity, where you can measure in the viscometer or rheometer, and this is where you plot the concentration of your material. If you plot log-log scale, and it's important to plot in log-log scale because we are trying to understand a scaling relationship. In other words, we are trying to understand N0, how does it scale with C concentration, and what is the scaling on the top of it. And you can see that there's going to be a region that your viscosity scale linearly with a log scale of C. And there's a region where you now see a big deviation as shown in the black dots. And this is happening when your polymers start to touching and entangle with each other, okay? So you can see quite distinctly there's two different regions. And with regard to different concentration, you can also see different polymer would show quite different behavior, but what common is they would show up this transition. And this transition point is going to happen to be where your polymers start to touching each other, and also defined as the overlapping concentration, okay? And in the previous work, we have one of the homework as shown here. This is where you can calculate the overlapping concentration. But as you know, this overlapping concentration will depend on the molecular weight as well as the characteristic ratio of your material. So I want to go through this one more time. It's pretty standard where you can understand what is polystyrene. You can calculate RG, you can calculate molecular weight and or the weight within that RG, and you can get the volume and you can get the concentration. So this is where polystyrene, it's about 58 grams per liter, also known as 58 milligrams per mil. This is where you start to have these coils overlapping each other, okay? But this also depends on the molecular weight, and the molecular weight will be influencing here because the larger the molecular weight, you have different coil size. There's more discussion regarding a different region, how do we understand the polymer's solution behavior, and I would suggest everybody to read Ralph Colby and Michael Rubinstein's Polymer Physics book. The other textbook I suggest in the syllabus, and in that textbook they dedicated one chapter to discuss what happened in the concentrated region. Especially in the concentrated region, you have different coil, polymer coil size and conformation. And as you can imagine, in the concentrated region, there's another parameter that is important called globular size, which is discussing about how much each components of your polymer coil can be regarded as good solvent, and in what region, when they overlap, they actually behave like in the excluded volume is screened, so it behaves like melt state. So looking at different scale, you can see different behavior in the concentrated region. If you are interested, feel free to go into that and take a look. If you have questions, I'm very much here to help. The other one I want to talk about today is about what is chi exactly. So in the textbook, you will see there's also dedicated a short chapter discussing about this chi parameter, okay? So in particularly this chi parameter can be also understood as different interactions within the species. And this can be discussed in the cohesive energy density parameter. And I will discuss just one slide about what is this. In this, we need to create a couple slides right here. So what specific is chi? We have discussed this throughout the lecture. We know this is something called Flory-Huggins parameter. And we know the chi parameter determines the interaction between two parts of molecular. Either it is favorable or non-favorable, right? So we have the system that we know it's if the chi is equal to 0.5 or 0.5, it's a theta solvent condition. And if chi is larger than 0.5, we know it's a good solvent from the previous discussion. But what is exactly this interaction? This can be understood at molecular level, what is interaction you having. So generally speaking, we can understand, going back to what we call a different interaction when we discuss the enthalpy, W12. Remember how we define the chi parameter is coming from this particular interaction, right? So we have different W values, and this W value can be generally defined as pair interaction between your two species. So this can be defined as just the two species at a distance of I and j. Sorry, this should be power of 6, and this can be generally defined as a dipole-dipole interaction. Okay, what is dipole? So this defined as what happens at two molecular. You always have polarization happens within a given species. So whenever there is polarization, this what happens, your molecular will start to show regions where is more predominantly positive charges, and there's regions it will be predominantly negative charge. So when you have formed dipole-dipole interactions, there is additional interaction happen at molecular level between whatever your molecular A, whatever your molecular B. Okay? This allows us to define what could be the interaction between two species. If we, generally speaking, when we talked about the enthalpy of our material, we have Z parameter, we have delta W. So these two are generally defined as W12 minus half of W11, half of W22. So W11 is interaction parameter, a pair interaction, whatever it is, between species A and B. And what W11 is basically with itself, AA molecular and BB molecular for that. And that's what is defines or help us define what is delta H enthalpy partially, right? So here, what is useful and interesting, because of the definition we gave here, we can easily simplify this particular relationship. And how can we do that is through a very simple math trick, where W12, as we know, is equally to alpha 1, alpha 2, R12. If we assume the distance is always the same between different species, then we can simply get this as alpha 1, R1 cubical multiplied by alpha 2, R2 cubical, which you will see this can be straightforwardly written as W11 multiplied by W22. So what this allows us to do is we now established a simple relationship between what is W11, so the pair interaction between molecular A and B with respect to the interaction of itself, okay? So if you know the interaction of AA species and BB species, and AB species is just going to be a root square of 2 and take a negative. This is extremely helpful. So now we can simplify Z multiplied by delta W into a very straightforward equations where we can now write this is going to be 2 W11 and W22 plus. We can write as W11 as W11, take a root square and multiply by 2. This is still going to be the same as W11 as we show in the last slides. And we can take a W22, take a root and take a square of it. And this now becomes a fairly straightforward writing of the difference between W1 and W22, take a root and get a square again. Now, why this is important, why this matrix is something we're discussing here is now, instead of getting the W interaction, as long as you know what is parameter W11 and W22, you can already know what is the enthalpy difference before and after when you mix them. And this is very nice. And what that means, if we have a table that lists what is interaction between all the different solvents by itself, then you can calculate out what is interaction between, for example, toluene and hexane, as long as you know the toluene interaction with itself as well as hexane interaction with itself. It's quite nice. And indeed, a lot of researchers has been thinking along this way, and they define a new parameter called interaction parameter. What that means is they can define a U interaction parameter upon evaporation. That means if you pull a molecule from its liquid state away from the majority of it, and this can be defined, this called a molar heat of vaporization of pure substance. So it's what the energy takes you to heat toluene and let it evaporate. This can be defined as an Avogadro constant multiplied by Z, then Wii divided by 2. So if we can define this, then what we show in previously, you can have very straightforward what is defined here between these two, right? This will allow us to get very straightforwardly introduce another parameter called cohesive energy density. This actually is a parameter you can look it up in any polymer handbook. So you can get a handbook and you can look it up what is cohesive energy density. It is related to what we have talked about, the energy evaporation. And there's quite some concept being defined here, but bear with me. It's very much related to what we have defined above. So this will be related very much exactly Wii to, except we need now normalize by a unit volume, and this will be commonly known as cohesive energy density. And this is shown here. And you can see these are very similar parameters, except that we need to normalize by a unit volume. Now, what you have seen in previous equation is very pretty. You can define chi directly based on this cohesive energy density. So this will be defined as cohesive energy difference, take a square. This delta 1, you can look that up from any polymer handbook. Okay? So delta 1, delta 2. If I know my toluene and if I know my hexane, what I need is just plug in, and R and T are, R is a gas constant, T is temperature, VI is a unit volume of your each molecule. So this way, the chi is very obviously, it's proportional to difference between these delta value. If I have two solvents has very similar delta value, that means I'm going to get a very little chi. If these two matches, then my chi will be 0. But if these two are very different and very far away, then I would get a very large chi value. In reality, this, based on a large set of the data, people actually found that your chi parameter is indeed proportional to this equation, but empirically, we overlooked many parameters based on this very simple dipole-dipole moment. So people need to have a modifier based on this particular equation. So people found that the data empirically need to add a constant to the end at 0.34. Using this, just the first part, you missed out some sort of unknown parameter. So take this with a little bit grain of salt. This is very much like an empirical equation, but it's a good start for you to know what is the chi parameter with two unknown species. So for example, you can start to look at different polymer pair. So for example, polystyrene and PMMA, you can look at what is delta for PS and delta 2 for PMMA, and you can start to get a chi value, and you will see this is very low chi. It is much lower than what is this empirical equation and prediction. And there's other cases where it's more suitable, is for example polyisoprene together with dioxane. This one is much suitable in terms of prediction. If you plug in what is delta 1, delta 2, and you will get very almost close to what is prediction based on experimental measurement. So if you have a new polymer pair you made in the lab, if you want to know a little bit of their chi and how to predict them, you can look up the polymer handbook, find the solubility parameter, or also called a cohesive energy, and this allows you to determine if your material is likely have low chi or high chi, although as I mentioned the value of it is going to be slightly different. So take a little bit of grain of salt when you looking at this empirical equation. Okay, so those two are the bookkeeping parts, and I just want to finish this before we have a summary of today's lecture. Okay, so let me insert and get a few blank pages so that we can continue to discuss. So we can have a quick summary about today's lecture and actually the whole chapter. So let's have a summary of what we have did for this whole particular chapter in chapter 7. In chapter 6, everybody has known that we mostly focused on discussion of the chain conformation. We discussed different chain model. We understand in what type of chain models and what the chain conformation will look like. We have covered different chain models like a free rotation chain, free joint chain, etc. At the end of the day, we actually know there's a couple parameters we can use, like radius gyration as well as others, can describe how big a given polymer coil will be. So this particular chapter discussed the thermodynamics of the solution. And throughout the lecture, I think thermodynamics plays a very big role. We discussed all kind of theories related to phase behavior. We start with very simple lattice theory, where we start with regular lattice with two species of the similar sizes. and you can visualize as two solvents. And then we started discussing more complicated case where Flory-Hagen series start coming, and where Flory-Hagen developed a way based on lattice theory where you now can understand what is a phase behavior for polymer. And throughout the lecture, we talked about different contributions of entropy and enthalpy, and those persisted throughout the lecture. Well, at the beginning, we discussed what is respective contribution from entropy. Remember that we discussed what is the delta S. Okay, so this would be a quick summary about what we did and before we finish the chapter. Okay, so we discussed what is delta S, and I think everybody should know by now this is proportional to number of different states where in this omega term, and that's fundamental. And we actually did quite an example using the lattice to count how many possible states if we fill the lattice with the white or black balls into the lattice, and this allows us to get what is the delta S, because we need to get is delta S is where the S of after we mix minus S before we mix in, right? So this is quite important where we got the value of the chi inside, sorry, not the chi, but the delta S, the entropy during the lattice theory in terms of mixing, where we have volume fraction or molar fraction, because they're the same if we assume the molar volume. Then you get x1 is volume fraction log x1 plus x2 log x2 in terms of entropy contribution. Throughout the first part, that's quite easy, right? Then we go into a little bit more complicated, from my perspective, into the enthalpy contribution. Okay, and then we discussed what is delta H, and there we define a Flory-Hagen's parameter. It's based on where the pair interaction between different species. We talked about W11, W22, and what's the possibility of a polymer or molecular, solvent molecular meeting another one, and that's where we get the parameter. This would be the chi, x1, x2, the volume fraction between two species, chi and multiplied by RT, and RT is gas constant. I guess we can keep it here, or we can let's use a KT here so that we matches what we talked about in the delta S. So this two combining together will allow us to understand a very important parameter we discussed in the phase diagram is what is delta G. The free energy changes is the key. No matter how great the enthalpy change or how great the entropy, they need to be considered together to get is what is the delta G, right? In terms of here, the delta G, you need to get from the whatever molecular system you talked about. Let's use the gas constant, use the KT, multiply. This will be x1 log x1 plus x2 log x2 plus x1, x2, and a chi. Okay? And very simple, elegant for the lattice theory, right? And based on this equation, in the later part of the lecture, we used this extensively to discuss what is the phase behavior for your very simple binary case, and we understand the phase behavior for solvents. Using this, it's a very good start, and it's very elegant in a sense that this equation is very symmetric and very pretty. You got x1 ln x1, x2 ln x2 plus x1, x2 chi, right? Flory-Hagens theory is built upon this very simple, elegant equation to give a modification in terms of entropy contribution in one of the components. So in there, your delta S is defined as contribution from the solvent again and contribution from the polymer. And we know because of connectivity, you need to know this in order to do well in the test, where we defined a new parameter phi1. It's pretty much like x1 in terms of volume fraction, but phi you need to consider the degree of polymerization for your polymer phase, okay? Phi1 is now the volume fraction for the solvents, and you now need to multiply by phi2 divided by n and ln phi2. Okay, so this will give you the entropy contribution, and we know the enthalpy will stay pretty much the same per lattice size. So you would get what is delta H will be kT multiplied by phi1, phi2, and chi parameter. And combining together, we get the Flory-Hagens theory, where delta G would be equal to kT multiplied by phi1 ln phi1 plus phi2 divided by n ln phi2 and plus phi1, phi2, and chi. So you can see almost identical, except the connectivity of your polymer give you this specific term that, as you can see, shown at the bottom. Quite nice. We understand what is free energy contributing from each individual species. Then we started with the last part of the second half of the lecture. In the chapter 7 is about phase diagram, and I want to go into too much detail because we know it pretty well. We talked about the phase behavior based on what is the Flory-Hagens. And in the quiz that I reviewed, quite some of you was confused about the difference between the delta G with phi versus another one is T versus phi. And these two are different, okay? And this is based on what is our Flory-Hagens series or lattice series tell you what is the delta G or your free energy before and after mixing depends on the phi. And if you look at equation here, we can define this as y. It's going to be a function of what is this phi1, right? So you plug in different value in the phi1, you can get what this curve is. And this is called free energy diagram. It's not the phase behavior. So on the right, then you can get a phase diagram where you can obtain what would be the phase behavior. But remember, this would be the T. T is temperature. And what this tell you is you can look up your polymer, look up at different concentration and different temperature, whether mix or not. So the phase diagram serves one purpose, is predict and let you know if your system will mix or not. So you can have region where we call it one phase and where you have two phase. So if I develop a new material, let's say polymer X dissolved at a concentration about 20% in toluene, if I know the phase diagram, then I can look it up. 20% is here, and you can see throughout the temperature range, it will be one phase, so it's fine. I can totally make this solution and it will be stable, but I can also look it up at 50% and it will be different. But in reality, as I mentioned, polymer will be different because of Flory-Hagens theory. Your phase diagram will be shifted to the left, and degree of shifting depends on proportional to dP or n value. So look at this new phase diagram. If you look at the polymer dissolved in toluene, this polymer X, then you might be able to see at low temperature where it will be sit in the two phase, but increase the temperature, it will sit in the one phase. So I can get a knowledge about what the processing condition I need to take in terms of mixing of preparing a solution. Okay, that would be a great example. And you guys also need to understand what's the difference between the spinodal and binodal curve. And remember, in the phase diagram, let me zoom it in, you would have two areas. So there, spinodal and binodal. This would be the temperature. This would be fine, and these are different. And in the spinodal curve, it is defined by the intercept of your free energy with respect to the tangent of the curve. So if you look at here, if I draw a tangent will intercept these two points will be defining what is spinodal point. But binodal point is more straightforward, where this is simply defined as second derivative of G free energy with respect to the phi, if it will be 0 or not. And that's the definition if you absolutely will have one phase or two phase. Okay? And within binodal, it is pretty much going to be unstable. So you're always going to have phase separation. But if you are sitting in the spinodal, if you look at delta G curve, they're tentatively stable. But if you have some disturbance into the system, it will still relax. So a great example here is where you have spinodal decomposition within the binodal phase. But here, it's not going to happen in spinodal phase, but you can have a nucleation happening. If you happen to have a nuclei, then they could spontaneously happen to phase separate and go from the metastable to the stable state. Okay. I guess this is pretty much summarized. Okay, there's one more thing that we discussed is what is UCST and LCST throughout the lecture. So you guys need to know the definition between these two. One is called upper critical temperature and lower critical temperature. So in this case, because the critical temperature is happening at the top, so it's a UCST behavior. Of course, you can, most of the time, the polymer will behave like UCST because the higher the temperature, it will dissolve better. But there's also a special case, like polynipene is a unique case where it's a temperature responsive, and at high temperature, it actually will behave phase separate and become cloudy. But those two are very common materials. And to summarize the last part, we also have a discussion of a new parameter called osmotic pressure throughout this particular chapter. Okay, so this parameter comes from the fact that when you have a polymer dissolved in a solution, you would also create chemical potential differences in the particular part where you have the polymer versus the part you don't have it. And this actually can be used to great advantage to polymer scientists. And in the lecture, using the free energy approach, we discussed how can we use the osmotic pressure to understand the polymer molecular behavior. And very nicely, there is a correlation between the osmotic pressure with respect to the molecular weight, as well as second Vary coefficient. You know, depend on textbooks. Some of them call it B2, some of them call it V2, but it's the same. It's a second Vary coefficient, and this, let's use B2, is related to the chi, right? We know that B2 will be half inverse minus chi. And it's a very good parameter for us to see if your system is in a good solvent, in a theta solvent, or a bad solvent. So you have scenarios when B2 equals to 0, larger than 0, and smaller than 0, where this will define as good, this will define as poor, and in the middle, that's going to be the Zeta solvent. To some degree, it's actually better than chi, because somehow chi needs to be related to 0.5, but B2, or secondary coefficient, can be directly used to understand what is solvent quality. It depends on the sign. Is it positive or equal to 0 or negative? And we know that there's another great way to use this is to get the molecular weight. If you measure osmotic pressure and plot is divided by concentration, please be careful. You actually have to divide the osmotic pressure by CRT, then you can get a linear relationship between the B2 count and there's higher order term. Actually, we usually don't even consider the third vary coefficient term, so this usually is eliminated. We can get a linear plot for pi divided by CRT, and it should be proportional to the C. The slope of curve will be the B2, and the intercept with y-axis at when concentration is 0 will be inverse of the molecular weight. This is pretty much also used to understand what is the solvent quality, and there's a couple homeworks we're going to discuss in the next lecture when we have this particular discussion this Thursday, okay? With that, I think we should be good to go for today's lecture. I'm going to ask everybody, if you have questions, please ask. Otherwise, the plan for next week will be for Thursday, not next week. For this Thursday, we're going to go through the homeworks and discuss the homeworks from 1 to 13. And I saw half of you turned in the homeworks. For those who have not, you missed the deadline, but you still have a chance to submit it. Please do so. Definitely before when we discuss this Thursday. And as everybody has known, that we originally was planning to have a test next Tuesday, but it looks like you have another deadline, so we're going to move it to Thursday. So the test will be next Thursday for the second chapter. On next Tuesday, we can start the next chapter in the polymer chemistry, and we will discuss what is the rubber elasticity. Okay, so any question on